All right. Well, I just got a warning message that my microphone is not working correctly. Let's see what happens with that. Um, Nothing would surprise me. All right. Um, so let's get back to where we left off. I had to interrupt the last recording, but we're going to carry on where we left off. So here we are. We have one more example in section 5B, or two actually, and then we'll move on to 5C, where we're going to be looking at the basic integration formulas, or at least some more than the ones we've already covered. So anyway, let's take a look at this one. So we've got the integral from 0 to 3 of 2x to the fourth plus 3x cubed dx. So we'll break it up into two different integrals, as you can see. And then the constants on the outside of each integral. And so we, based on the power rule, we'll have 2 times, in the first case, x to the fifth over 5, evaluated from 0 to 3. And then in the second case, we have 3 times x to the fourth over 4, evaluated from 0 to 3. Now, of course, even here, we could do a little bit more rearranging if we wanted to move the 1/5 from the first case outside and the 1/4 in the second case outside, but it's not absolutely necessary. But what I would like you to see here is that what you're actually doing here is you're solving for f of what we are calling f of 3. Capital F of 3 is the integral evaluated 3 down to the negative infinity, and then this is f of 0. So the difference between the two is what we're actually looking for. We're only interested in the area between 0 and 3. Okay, so the difference between these two integrals will give us the area that we need. And then this is also f of 3 for this function. Or yeah, for this function. And then we have f of 0. But I mean, algebraically, this is exactly what we've been doing all along. So if you plug in the correct numbers, you'll see, after a lot of pretty messy algebra, I must say, you'll ultimately end up with, yeah, it really was kind of messy. We ended up with 3159 over 20. All right, okay, there's one more here. So here we're looking at 3e to the x over the area from 0 to 1. That would look something like this. Okay, so we can rewrite this. We can move the 3 outside. Of course, the integral of e to the x dx is just e to the x. Well, actually, in this case, it's also plus c, but since we're now calculating a definite integral, we don't have to worry about the c. So instead, we're evaluating our result from 0 to 1. So we've got 3 times e to the first minus e to the 0, which is the same thing as 3 times e minus 1. And then we can leave it like this if you want, but you could also write it as 3e minus 3. Now, here's an interesting one, because this is the exception to the power rule. Remember the way the power rule works with integrals. For n equals unequals -1, but of course here we do have n equals -1 because 1 over x is equal to x to the minus 1. In that case, we have log absolute value of x plus c. All right, and now here, of course, we're interested in the definite integral from 1 to 3. So that would look something like this. All right. And so what you're going to have here then is that when you integrate, you'll get the log of absolute value of x evaluated from 1 to 3. So you've got natural log of absolute value of 3. Now, of course, 3 is a constant. It already is positive. We don't really have to worry about the absolute value in this case. And also, don't forget the log to any base of 1 is just 0. Because no matter what the base is, b to the 0 power equals 1. Okay, so we ultimately just end up with a natural log of 3. All right. I think this is the last one. This one is a trig question, so we have to be careful. Now, you might recall from other chapters that the integral of sine x dx is actually the negative cosine of x plus c. All right, here we're evaluating it from 0 to pi, though. So we don't need the constant. Okay. So then this is what we'll end up with. So we'll have the negative cosine of pi minus the minus cosine of 0. And that's going to be the cosine of pi is 1. Wait a minute. Negative one. Hold on. Let me get my calculator out. Hold on 1 second. I just want to double check because I didn't make a typo or something. The cosine of pi, remember, oh, by the way, if you're going to use your calculator, whether it's the TI-84 or the CE, don't forget that in order to calculate the cosine or the sine of a radian measure like pi, you have to be in the radians mode. So at the top, there's a mode button way at the very top of your calculator, right there. Now, of course, I recognize that when I show this to you on the screen like this, it's going to be backwards. But yes, it's next to the second button. It's this one right here. All right, so choose that, and you'll see there's a huge menu there. Go down and find the one that says radians and degrees. Make sure it's in radians. If it's not, scroll over and select that with the enter button. And now you can go ahead and say cosine pi. The pi button is found directly above the exponentiation key, which is itself directly above the division. All right, so now we're looking, see that? Directly above it, the second of that button, second function for that button, it is pi. So you're basically hitting second exponentiation key, and then you'll get pi, and then sure enough, it's -1. Okay, I just want to make sure. Okay, and now my tablet doesn't want to work. Oh, here we go. Cosine of 0, while we're at it, let's double check cosine of 0. That's going to be +1. So what do we have? -1 plus, actually -1. So yeah, ultimately it's 1 plus 1, which is 2. Okay, that's good. Very nice. All right, so that's it for this section. So we're going to dive into 5C, where we finally get to look at some of these very, very important integration formulas. Now, I think I pointed this out to you before. If you look in the book, there's a huge list of these formulas in one of the appendices. So I'm going to go open it up for you so you can see what I mean. It's huge. It's much, much longer than the list of derivatives. That's for sure. And that's because, I mean, let's face it, integration is just a more complex operation than taking a derivative or a differentiation. So it stands to reason that the appendix is going to be that much longer. All right, here we go. So we're looking at, here it is, Appendix A. So this is the list. And you can see it's quite long, quite extensive. But there's certain rules that we can learn to sort of reduce the complexity of this process. Oh, it just goes on and on and on. I mean, God, look at this. And so a lot of times the challenge with integration is recognizing which case we're looking at. And if it's not one of these, often we can use algebraic tricks, I guess you would call them, to sort of rearrange the integral into something that is actually falls into one of these categories, so that you can actually go ahead and just use one of these cases. So anyway, let's start to take a look at them. Now, here's an example. What if we had a mess like this? It looks like we're going to have a lot of trouble with this. So here's something we could do. Let's already, right off the bat, use algebra to rearrange it into something simpler. Now, in my opinion, you should always take roots, or radicals rather, and turn them into roots of some kind. In other words, the square root of x, I would rewrite it as x to the 1/2 power. And I'm just going to multiply them out. X to the 1/2 plus x to the 1/2 plus x to the 3/2, because I'm multiplying x to the 1/2 times x to the first. That's going to be x to the 1/2 plus 1, which is, of course, x to the 3/2 dx. All right, now we can break this up into two separate integrals, and we can apply the power rule to each one individually. And I think you'll agree that's the way to go. The way it was written before, it might have been one of these special cases, but imagine yourself just looking through the list to find it might have been a challenge. So if you can think of a clever way to avoid that, you should always go for it. Okay, so you can see here, we've got two separate integrals, which clearly lend themselves to the power rule. All right, let's do it. So we have for the first integral, x to the 3/2 power over 3/2. For the second one, we have x to the 5/2 power over 5/2. Now, again, as you've seen before, when you have division by 3/2, it's equivalent to multiplying by 2/3. I think you'll agree this is much, much easier. And over here, dividing by 5/2 is the same thing as multiplying by 2/5. You've got the exponent is 3/2, 5/2, and of course now we're evaluating from 1 to 4 for both of them. So let's run through that. So, of course, in this first case, I'm evaluating this function at 4 and 1 and subtracting 1 from the other. Okay, so in other words, let's say for no matter what function you have here, this is what you're doing. Okay, so in other words, here we have 2/3 x to the 3/2. So the first term will be the x is replaced by a 4, and then the second term is replaced by 1. We subtract 1 from the other. In the second case, again, the x is replaced by a 4 here and a 1 here. So in the first case, we have 4 to the 3 halves is basically, it is 4 cubed, the square root of 4 cubed. So if you, what you can do to solve for that is either go directly to your calculator and let your exponent be 3 halves. The other option is to take 4 cubed and then square root it, the result. All right. Now, by the way, on this calculator, if you're going to use a fractional exponent, you may need to use parentheses to surround it. I think for this calculator you do. I'm going to try this 4 raised to the 3 halves power. I think it'll get confused if you don't. So 4 to the 3 halves is 8. So this calculator, the TI-84 series, you would hit 4, there's your exponent. You would put then open parentheses 3 divided by 2. And then, of course, at the end, you have to hit the enter button. And that will give you your result, which is 8. Now, of course, we don't just have 4 to the 3 halves here. That is multiplied by 2. And then we're dividing it by 3. So you got 16 thirds. Of course, here 1 to the 3 halves power is just 1. So you've got negative 2 thirds. 4 to the 5 halves power is 32. And then, of course, is being doubled because this 2 is here. So you got 64 over 5 minus 2 over 5. And now, when you combine them with the common denominator of 15, ultimately we end up with 256 over 15. Now, it just suddenly dawned on me, I've never attempted to do a definite integral with Symbol Lab. I'm kind of dying to see how it works. I tell you what, let's go to Symbol Lab for a second and challenge it with this one. I assume that it's capable of doing this, but you should never assume anything in technology, that's for sure. So let's try this. Now, I don't think. Oh, here we go. It's got the symbols. It's got to be okay. 1 to 4. And then we have the square root of x. X plus 1 or 1 plus x dx. Now, the only unfortunate thing is that it's possible that they could give it to us. No, it worked out the same. Okay, beautiful. Sometimes, though, you can get the same answer and you don't even realize it because it's a very messy algebraic rearrangement of it. But since this is a constant, there's not much they can do about that. There is there. Also, don't forget, it has the capability of showing you at least some of the steps. It looks like they've done what we did. They broke it up into 2 separate integrals and then, well, they didn't really fill in they didn't tell us to use the power rule here, which I think is kind of weak, but oh, this is nice. They're showing us graphically what we've just accomplished. Look at that. So we're looking at the area between 1 and 4 for this function. All right, well, at least that's a nice feature. Okay. All right. Now, the net change theorem shows that when a quantity changes, the new value equals the original plus the integral of the rate of change. What does that mean? All right. This is what they're telling me. So basically what it means is this. You've got a function like we just had. It's essentially telling us the reason why we can solve for an area with integration. That area could be written as the integral of the function at 4 minus the integral at 1. That's what this is telling us. It means the same thing as doing this. That's really what this is telling us. So anyway, suppose that an engine is turned on at time t equals 0, and the rate of consumption of gas is 5 minus t cubed for the first hour. How much gas is used during that hour? So you could visualize this as being an area under a curve. In fact, why don't we go to Symbolab and see what this thing looks like? Just so we can visualize. What do we have here? The function is 5 minus, first let's just graph the function. F of t, we'll call it equals 5 minus t cubed. So we'll see what that graph looks like. And remember, we're only interested in the area between 0 and 1, the first hour. Okay. So I guess that would be this right here, the area in the curve between these two. Of course, if you notice that it is shrinking as time goes by, but here, this is what we're after. So we'll integrate over that interval using the same techniques we just did. We'll break this up into two terms and evaluate from 0 to 1. We'll use the power rule, of course, in both cases. And when we do that, we'll have 5. We just repeat this value here. So this is what we're actually doing. Okay, within each one, we're evaluating what's inside the brackets at 1 and then doing the same thing for 0, and then we subtract. $19. Okay. Okay, now here's an interesting discussion. There actually are two types of functions that we may encounter. We have what are called even functions and odd functions. So what's the difference between the two? Well, an even function means f of negative x equals f of x. So, for example, f of x squared. F of x equals x squared, rather. F of x is obviously x squared. F of negative x is negative x squared, which is x squared. So this is a perfect example of an even function. And you can tell by looking at a function graphically, even functions I don't want to overgeneralize, but you could tell because the left and the right-hand sides are balanced, okay? So in other words, you can see what's going on the left-hand side here is the same as what's on the right-hand side. So there's a symmetry between left and right with even functions. What about an odd function? What is that? Well, this one tells us that if negative f of negative x equals the original function, then that means this is an odd function. So here's a good example. Y equals x cubed. Why do I say that? Because, or actually, I'll write it as f of x. Negative f of negative x would be negative x cubed. And of course, negative x cubed is negative. So you just end up with positive x cubed. So with this kind of function, there's symmetry again, not from left to right, but with respect to the origin. In other words, here you've got this function that's entirely in the first and the third quadrants. The first and the third quadrants are mirror images of each other. Reflection, imagine it's like a reflection, but the origin is where they're reflecting. Now, most functions are neither even nor odd. I mean, you could try a bunch of different functions and you might not find any that are even or odd, but some functions are even and some are odd. And sometimes the way we go about a process may be different for even and odd functions. All right, now, the integral of an even function whose limits or limits of integration are from negative a to a can be broken down into two equal parts. Okay, something like this. How do we do that? We can break it down with respect to 0. So in other words, what we can do is rewrite it as but because of the symmetry with respect to the the vertical axis, these are both equal to each other. So what that means then is that what you've actually got here is 2 times either one of these. You can choose one of these and you just note that you're just doubling one of them. And that might make it easier to do the calculations. So for a continuous even function from negative a to a, integrated from negative a to a, we can simply rewrite it as 2 times the same integral over the interval 0 to a. An odd function is a little different. It turns out that if we do this with an odd function, though, these two will have the opposite signs. They'll be the same value, but with opposite signs. So this is going to equal 0. Interesting. So, so for the even function, we just have double integral from 0 to a. But with the odd function, it's just 0. Okay. So how about this one? Now, this next function, 3x to the 8th, Well, you don't see exponents that high very often. This is not with practical applications. No, not really. I mean, if you're dealing with real applications from the real world, it's kind of unusual that the exponent gets much above 2 or 3. It's very rare. But here we've got 3x to the 8th. Now, how can you tell if it's even? Because let's say you take f of x is 3x to the 8th minus 2. F of negative x would be 3 negative x to the 8 minus 2, which is still 3x to the 8th minus 2, which is the original f of x. Well, there's a negative number raised to any even exponent will just be a positive exponent. So this is an even function. And you can see from this graph, it is symmetrical about the vertical axis, the y-axis. So we're going to integrate this thing the way we usually do with the power rule. And we can break it up into 2 components and solve it with the power rule. So we have 3 integral x to the 8 dx minus 2 integral dx, evaluated from -2 to 2. So then what you can do is do the substitutions. To the 9th is 512. Now, -2 to the 9th is going to be -512, but we're subtracting it. We have 2 plus 2. So that leaves us with, on the next slide, 3 times 512 over 9 minus a minus 512 over 9 minus 2, parentheses 2 minus minus 2. So we've got 3 times 1024 over 9 minus 8. This turns out to be 8. And when you find common denominators, you'll see that you ultimately end up with 1003. Now, here's what we want to know. Did our rule work? All right, let's find out. So since the original integral was from -2 to 2, what we want to know is it true that this is equal to double this integral? All right, so if you evaluate the one on the right from 0 to 2, well, it's the same integration, the same power rule. It's just that now the range of integration is from 0 to 2 instead of -2 to 2. You plug in all the values. You can see that you ultimately wind up with, well, it says here 3,000 over 9, but it's 1,000 over 3. So in other words, it did work. Okay. So in other words, yes, we've just demonstrated just by reintegrating it again a second time from 0 to 2, but then doubling the final result. It turns out that this was absolutely correct. And that's what we would expect. Now, if you're trying something else, like let's say it had been something like this, well, then you can't really, then this doesn't work because you've got to the wrong interval, the wrong range. But when it's the exact same amount below zero and above, then we can use this principle. And this is the graph that shows you exactly what we just demonstrated, that the area that we are interested